Hello everyone. Today we're going to be wrapping up gears for real. So we're going to start talking about gear trains. We'll talk a little bit about differential. It should be a short lecture, but it was a good break from the material we covered in the last lecture. A gear train is just a series of gears. So a simple gear train is where we have an input gear, we have an output gear, and then there's just one gear in between. So in the next, we'll go from here to here to here to here to here, and we don't have gears on common shafts. That would be a compound gear train. What you need to know about simple gear trains is when I do the velocity ratio for this, when I look at the ratio of gear 2 and 3, so that would be here, gear 3 and 4 here, 4 and 5 here, 5 and 6 here. Note what happens. Those cancel, those cancel, those cancel, and all I'm left with is the teeth on the first gear and the teeth on the last gear. So the only thing that matters, so I guess there's two things that matter in a simple gear train. It's the number of teeth on the input gear, number of teeth on the output gear, and how many transitions there are in between. So each time I have a gear pair here, there's a negative in the velocity ratio. So in this case, the velocity ratio would be negative, positive, negative, positive in this case. So the tooth count in the middle here, it doesn't matter at all from a ratio perspective. So you might as well use all the same gear just to keep them cheap. The only reason you might not is if you need to break off something else to go somewhere in another direction, somewhere in the middle here, or maybe you want to bend around a corner and you need to put a bigger gear here, a smaller gear here, something like that. But from a velocity ratio perspective, the size of the gears in the middle don't really do anything. So it's input, it's the output, and then the number of pairs there are to get the sign on it. So it's input over output, and then you have to figure out if it's plus or minus. Compound gears. So compound gears, so if I actually want to get a lot of ratio, that's where compound gears come in. If I need a 100-to-1 ratio, it makes no sense to use a simple gear train because it's all about the first gear and the last gear, and I need the output gear to be 100 times bigger than the input gear. Compound, I actually get compounding. So I have an input shaft, I have an output shaft that's got two different gears on it, one that mates with the input gear, and then one that's connected to a smaller pinion here that goes to the output shaft. The velocity ratio for this, so it's going to be N2 over N3 for this reduction, or multiplication. I guess that'd be reduction, would be what that'd be called. And then this to this, for this reduction, would be N4 over N5. Now, N3 and 4 are spinning at the same speed, so I don't need to have a ratio for those. It would just be 1 to 1. So in this, I actually get some multiplication, and this can be generalized as the product of the teeth that are driving. So this gear, N2 is driving N3, N4 is driving N5, so it is N2 times N4, the product of the driver, divided by the product of the driven. So N3 is being driven, N5 is being driven, so it's the product of the driver over the product of the driven, and again you have to figure out the plus or minus side. So here it would be a minus, and then here it would be another minus, so it would be plus. They'd be churning in the same direction. Omega 2 and omega in and omega out would be the same direction. Reverted compound. So in some situations you want the central axis of the input and output gears in a compound gear train to be the same. There's a few good reasons for this. One is you can have these shafts run concentric to each other and have some kind of a bearing between them to help these things run to help resist the side loading. If I just put this in as shown here without anything connecting these two gears, then this is going to, the axial load that's going to try to spread these gears up and this counter shaft down. The counter shaft's fine. It's got some material between it to resist bending, but here I don't have anything to resist this bending load, and I get single shear out here, and these bearings are going to be very heavily loaded. If I put an extension on these two things and put a bearing between them, I need to put a bearing between them because they're running at different speeds, but it can help share the load a little bit here, and especially if I put a bearing from the case in the center here, a common bearing from the case. So it might just help share load a little bit better. For packaging, it might work a little better. This is very common in automotive applications. One real reason in automotive applications is most transmissions, these are usually manual transmissions, is where you see reverted compounds. In a manual transmission, you want to be able to have a 1-to-1 ratio where the input and output are spinning at the same speed. And if they're on a concentric shaft, then you can just clutch this guy to this guy and get it to run. Now, you might be wondering, what do you do about the countershaft down here? In a manual transmission, they don't actually move the gears around. There's some that you do, but in the vast majority of manual transmissions, you're not actually moving gears. What you're moving are little clutches that clutch the gears to a shaft. So in a lot of transmissions, the countershaft, all of these gears will be fixed to the shaft, and these gears will actually be able to be connected to the input shaft. This will be able to connect to the output shaft, and maybe these could connect to each other, and obviously you'll need more gears for multiple ratios. Like you put an extra gear here and an extra gear down here, and you could select which one of these two was clutched in, and you'd get different ratios depending on which one was clutched in. If you had two on your input, or two pairs on your input, two pairs on your output, then you could have a 5-speed transmission. If you could select this one or this one, that'd give you 2 speeds. This one or this one, that'd give you 2 times 2 speeds. And then you could clutch the input and output shafts together and not have the gears connected to the shafts. And you'd have your 5th speed, which would be like a 1-to-1 speed. You could add a reverse too, but you're going to have to add an extra gear. So there'll be 2 gears here that have a little idler gear in between them. That will provide the, so this would be a negative, this would be a negative, so you get a positive velocity ratio. If you put a little idler gear in between these, you get an extra reversal, and you get your reverse. And then your straight through would obviously be a 1-to-1 velocity ratio too. So you see reverted compound in gearboxes. For those, the radii have to sum, right, into pairs. Like or R2 plus R3 has to be R4 plus R5, right? That's the geometric constraint. Multiply that all by 2, the diameters all have to be the same. If you're using all the same pitch diameter gears, then the pitch diameter is N, number of teeth, over diameter. I can solve this equation for diameter and then plug it in here, and I get this. Now, if they're all the same pitch diameter, I can get rid of the pitch diameter, and N2 plus N3, tooth count on gear 2 plus tooth count on gear 3 has to be tooth count on gear 4 plus tooth count on gear 5. That assumes the pitch diameter is the same. Now, the diametral pitch. The diametral pitch of N2 and N3 will be the same. The diametral pitch of N4 and N5 will be the same because they're meshing. They have to be, otherwise the gears will eat themselves. So, for sure, these two will be the same and these two will be the same. But you might use different diametral pitch gears. Yeah, diametral pitch. Keep mixing up pitch diameter and diametral pitch. It's an easy thing to do. This is pitch diameter. This is diametral pitch. So you'll see in transmissions where different pairs will have different diametral pitches. And so for that, you'd have PD1, PD1, PD2, PD2, and you'd still need this relationship to hold. So you'll have to pick values of N2, 3, 4, and 5 that will satisfy that, and you get into sort of a constraint programming exercise that, since you can only have an integer number of teeth, it actually can get pretty interesting, the math on that. But if you want to keep it simple, you just use all the same pitch diameter, and then you just have to make sure these counts held, and that's easy to do. All right, you can use 13 and 15 and 12 and 16. All right, another gear application is differentials. A differential allows independent motion of 2 driven shafts. These are interesting. So obviously the main use for these nowadays is in cars. When you've got 2 wheels and you've got a car that needs to go around a turn, the inside radius is shorter than the outside radius, which means the outside tire, the outside wheel, needs to move along a longer arc, which means the shaft needs to turn more, or the tires slip. Those are the only options, is one tire turns more than the other, or one tire slips. So it's usually more comfortable and easier, especially at lower speeds and higher turn. The more the difference there is between the radii, the inside and outside tire swing, the more this is an issue. So at high speed, this isn't a big deal at all. Going around high speed turns, there's very little difference in the input inside and outside. But low speed turns, there's a lot of difference, and you need some way of allowing the inside and outside to move with respect to each other. And that's what the differential does. Looking inside the guts of a gear-driven differential like this one, there'll be end gears or side gears. These will be splined to the axle shafts. There'll be these two little gears here called spider gears. Those will be connected to a spider shaft to the differential housing, and then that will be bolted to the ring gear here. There might be some old ones where there's these little bosses that connect to spider gears, but what you'll see in most is that the little spider shaft here is connected to some kind of a housing that will then have a bolt pattern that connects to this pinion, so the ring gear, and the ring gear will be replaceable. Done that for a few times, you can change ratios by swapping out these two gears. Now they have to be set up correctly. This would be a hypoid gear set in most cases. This looks like a spiral bevel looking at the axes, but in general these will be hypoid gears. And you have to set the axial location of the ring gear, the axial location of the pinion, to get the teeth to contact in the correct location. You actually put a little paint on these teeth and spin it around and see what your tooth contact looks like. And then you use a dial indicator to measure backlash up here on your ring gear. And you have to do that until their tooth contact's good and your backlash is good. It takes a lot of iterating. It's very frustrating, I will admit. And if you get it wrong, this thing will eat itself very quickly. It'll be loud and then destroy itself, from a very short period of time to maybe a few thousand miles. You do it right, these things will last essentially the lifetime of the car, as long as they're properly lubricated. If not, then they also die pretty quick as well. But anyway, so if we look in here, if the input is fixed, I can actually turn this gear and the little spider gears turn, and then this gear turns in the other direction. If I fix this shaft and turn this shaft, then the pinion turns the ring gear, that turns the spider shaft, and that moves these little guys. Well, this guy will be fixed. Well, that means this guy over here ends up moving, but this guy is fixed. And I can hold this guy, and this guy turns, and this guy is fixed. So what you'll find is that the output speed for this, through the velocity ratio calculations on this, the sum of the outputs is equal to twice the input. Or you could say that that essentially your input is the average of the outputs, right? Divide by 2. The input is the average of the outputs. Now, you're usually in automotive applications, you're driving over here. So this velocity ratio has to be maintained. For a geared differential, this has to be true. And just from simple torque summation, just not creating torque out of thin air, the torque out plus the torque out over here has to be the torque input on the ring gear. And that's not the input in the pinion over here. You'd have to actually put the ratio here into it. So this torque input would be the torque over here that actually gets to the ring gear. So just a simple statics here, assuming the mass of the components is negligible, which is a pretty good assumption in this case actually. The torque on this shaft plus the torque on this shaft has to be the torque on the ring gear. For open differentials, there's no way of putting torque on one shaft without putting torque on another shaft. It's just the nature of the torque summation on these spider gears here. Since you can't resist their turning, there's nothing to resist these things rotating. The force over here's got to be the force over here, just because there's no place to put. There's no place to I mean, that's all there is on it, right? If you look at the forces on this thing, there's a force here, the force here, this thing's going to rotate. So these things rotate to make the torque the same on either side. So what that means for an open geared differential like this is if one tire has less friction than the other side, then you're going to be limited. The total amount of torque you can put out is going to be limited by the lowest one, since they're going to be the same. So whenever one axle starts to spin, whatever torque it takes to get that thing to spin is the same torque it's going to be on the other side. And that's going to be the limiting factor. So in limited slip differentials, you can bias the torque. You can put more torque on one side versus the other side. There's a lot of different ways of doing that. The main thing to know is for geared differentials, this ratio is always true because it's gears. You have to be breaking teeth off for it not to be true. This is going to be true for all differentials. I'm trying to think if there's any cases where that wouldn't be. It's going to be mostly true for all differentials. There might be a little bit of fudging in here where you're making some heat in here. But again, it's going to be, unless you are putting friction brakes between the differential housing and the ring gear, this is going to be true. And so the only exception I can think of to this would be where you're using brakes to do the differential action, or to brakes to do the limited slip. You have to include the braking torque in there, and that's a thing, by the way. So actually that's a really good thing. And with modern 4-channel anti-lock brake systems where all 4 wheels have brakes that can be controlled independently, you can use the brakes to break this relationship here. So if you've got a wheel that's spinning, you can apply the brakes on that side. That increases the torque on this shaft, which means that the torque on this shaft increases, and you can get out of whatever situation you're stuck in. That's something that in the early days of anti-lock brake systems, they were crude enough that didn't work very well, but the modern, very fast, high-speed anti-lock brake systems and the computing horsepower behind them, that actually works pretty well. It's a pretty good solution, actually. So, and you don't have to have a lot of complicated mechanical guts in here. You're using stuff you've already got on a vehicle. So, honestly, using the brakes as your differential or limited slip differential it's a pretty good setup if you do it right. So that's not. I mean, I actually own a truck that does that, and it's the bad system, and it doesn't work at all. And I've replaced this open differential with a proper limited slip differential. But there's some very high performance street cars that use the anti-lock brake system as a differential action. Some race cars too. So you could do it in a truck too. You probably want something mechanical in a truck, but it works for sure. So that's the main thing on limited slip is you just are getting different torque on these 2 shafts. It's still going to sum up to the input torque in almost all cases, but you're just changing what basically the minimum torque is by making them closer to each other. A lot of different ways to do that. The Detroit locker is one such method. Now this is not a geared differential, so a Detroit locker is more of a cam system or a clutch, where you have the spider assemblies rotated by the ring gear, and then you've got these little clutches that send torque to the tires on either side. So it's not geared. So if this is slipping on this, then this velocity ratio here is not maintained. And if these things are both locked together, then you can send torque all to one side or the other side. And that's really the characteristic of a Detroit locker, is when it's locked, the whole left, right, center are all locked together, and they're all spinning at the same speed, and you can send all the torque to one tire. Now, you still need to go around a turn, so these things are designed so that they're allowed to move with respect to each other when they're unloaded. So essentially what these things do is when you're putting torque on the spider assembly, it locks. When you're not putting torque on the spider assembly, these things can move with respect to each other, and your wheels can sort of cog with respect to each other around turns, which makes this very notchy and loud, and it wears a lot. These are good for drag racing, where you want to go in a straight line, but you still want to drive your car home and still want to drive it around parking lots. Detroit locker works really well. If all you're doing is drag racing and you're not driving on the street at all, you can just skip this thing, lock the left and right together. And they do that in a very redneck way by welding these things together. You'll see this on bad car shows, some good car shows too, where people are just in a hurry, but where you weld these together with a MIG welder, and you get yourself a spool is what it's called, but or a solid, spool where basically the whole thing's just locked together and the differential's not doing anything. The advantage of doing that is the car goes in a straight line. It can put all its torque down to one side, and one wheel just won't slip. One tire has to slip in a straight line, and they both slip or they don't slip. So for drag racing, straight line, that's great. For climbing hills on low coefficient of friction surfaces, that's great. For anything else, it's terrible. So you see, the Detroit locker is sort of the simplest differential that gets you that, where you're on the gas, both tires lock, or wheels, the left and right side lock, and you go in a straight line. when you let off the gas, you can go around turns. And it's simple. It can be made nice and strong. It's not good for road racing or performance street driving around turns or anything like that. But for going straight or off road, it's not terrible. Then we get into the fancy ones. So these are the torsion, true track, or helical styles, the general style for these, where they're actually worm gears. So we've got these little side gears here, and then we've got these little worm gears. So 3 on this side that mesh with 3 on this side. There's various different ways of doing this. But essentially, these act like worm gears. And so just like worm gears, if this helix angle is extreme enough, these things will actually wedge. So the way these things work, instead of locking like a Detroit locker, when I apply torque to the center housing here, the torque gets passed through these guys through here. And so what in this case, in a straight line, it's going to send torque to both sides. And if one side starts to slip, then depending on this wedge angle here, you can actually get it to take a little bit more torque before these things will actually allow to slide with respect to each other. And so they're geared, so the velocity ratio thing is going to be maintained. But when it starts talking about sending torque, it's almost like a little bit of preload on these teeth before they'll start to back drive. And you can actually send more torque to one side versus the other. So there's something called torque bias ratio on these, which is how much more torque you can put on one side versus the other. So 2.5 is a pretty common number for a simple true track or torsion like this, where I can put 2.5 times more torque on one side than the other side. Now, I can't fully lock these things up. They have to be able to be back driven, or they don't really work at all. They're not really a differential. So you have to be able to back drive them. So there's going to always be some point where one tire will spin versus the other one. If there's 3 or 4 times less friction on one side than the other side, then one tire will slip versus the other one. There's a clever trick you can do with these so like if you're off-road, if you're using one of these in a pickup truck or a Jeep or something off-road, and you're in a situation where like one tire's on asphalt and one's on sand, and the tire in sand is the one spinning, you can actually apply the brakes a little bit. Just apply a little bit of brakes, increases the torque that's on this side, that increases the torque on this side, and you can actually go forward. So these are what are used in the front and rear differential of Humvees. And that's one of the tricks you can use in a Humvee if it gets stuck, since it's all helicals, is you can just apply a little bit of brakes, and it increases the torque on both sides. So like 100 foot-pounds of braking here can give you 250 foot-pounds of braking here. So because of the torque bias ratio, so it works. That trick works really well on helical differentials. These are very smooth. There's no cogging on them. They're very efficient. They can get a little warm under heavy use, but all differentials will. There's no friction clutches that need to be worn and replaced, so these things will last a really long time. As far as mechanical differentials that are completely passive, they're probably the best. They're certainly the simplest. So it's the best plug-and-play differential there is especially for road racing. For road racing, there's not a better plug-and-play differential than a torsion, especially if you have bad drivers. You can't really adjust these. That's the biggest downside. Is you put them together and they do one thing, and they're designed to do that one thing, and they really need to be you need to really change this angle to get a different torque bias ratio, and that's not something it's a simple swap, right? You have to literally change the whole thing to do it. So but as far as just plug and play goes, they're great. They work off-road too. You see these in a lot of off-road vehicles and a lot of off-road racing series, especially front differentials. They work good, and center differentials too. So you see them a lot in center differentials and all-wheel drive setups. It's just a really, really, really good differential. And that's what I put in my truck when the open differential wasn't working, and it's literally fantastic. That's what the Formula Electric team did. The first couple years at Raw, the first couple years they used this style of differential because they didn't have good drivers, because they had people that never driven before, and it's just the simplest, basic kind of differential that works well. Posit traction, track lock, etc. This one goes under a lot of names. Still a geared spider gear differential. What's different here is you actually have some clutches that clutch the side gears to the casing. So the casing that goes back to grab the spider shaft here, you've got these clutches. And what happens is when you apply torque to the spider gear shaft here through the differential housing to the ring gear, so ring gear to differential housing to spider gear shaft to these gears, uh, they're going to push against these side gears, and there'll be a spreading force that pushes the side gears out, and that puts force into these clutches, and that force allows these clutches to resist torque. And instead of the left torque being equal to the right torque, it allows you to share some of the lowest torque with the highest torque. The torque gets passed through the clutches into the housing, back through these clutches back into this gear. So essentially you're clutching these two gears together. Now you could put the clutches in between the side gears, but usually you've got stuff there that prevents you from doing it. So instead of just putting clutches from the left side gear to the right side gear, you run the clutches to the housing and then back around here because you can package it. Salisbury, similar operation. Here, instead of using the wedging of the gears on each other, what you do is you have these little cams. So it goes ring gear to differential housing to these cams, to the spider gear shaft, to the side gears here. And so the spider gear shaft can actually wedge on these little ramps here, and you can have different wedge angles on these things. And so these are adjustable. You can get different cams here, and you can change how much wedging force there is and how much these clutches lock up, depending on how much input torque there is. And the coolest thing is you can actually change it for forward versus reverse, or driving torque versus braking torque. So under acceleration, you might really want to lock the tires together, so you'd have a really shallow ramp angle here, and that would really wedge a lot and send a lot of torque, and make sure the torque on the left and right are very close to each other. And then under braking, you might not want to lock. You might want them to still lock up a little bit, but maybe not a whole lot, so you'd have a steeper, and there'd be less wedging force. And so that's why these are, they're not as simple, not as plug and play, and they wear because these clutches always wear. But they're adjustable. So as far as adjustable mechanical differentials go, Salisbury is pretty well the king of adjustable mechanical differentials. So you see these a lot in racing where you really want to adjust the lockup and how it ramps between input and output. These will also have some springs on either side that'll provide some preloads, so these wedges will be preloaded, or these clutches will be preloaded to some extent. That's true on these as well. Sometimes you see a big S-shaped spring in the middle. The track locks have a big S-shaped spring in the middle. Excuse me. On Salisbury, you'll see what's called a Belleville washer, which is essentially a cup-shaped washer like this, and that acts like a really very stiff spring that provides the preload. And you can swap out those Belleville washers, or maybe you've got a ring that you can thread and move and pre-tension that Belleville washer and adjust the preload on them. But they're adjustable is the point. You get some weird ones like cam and pawl. So a cam and pawl mechanism is, I've had a diagram of that way back in maybe lesson 1 or 2. But a cam and pawl is essentially, it's like a one-way mechanism. So the cam can move one direction, and then the pawl is going to lock it. And then when it tries to move the other direction, it locks. So it'll move one way, but when you try to move it the other way, it locks. And the different ramp angle on these little pawls here and these face cams here allow this to move relative to it one way, but not the other way. And the end result is I drive the center here, I transmit torque to the pawls, and the torque gets, so you can see right here when I'm rotating it this way, there's one ramp angle versus the other way. So when I move it one way, it's going to bite into the pawls on either side and transmit torque to either side. So when I'm driving it, these things lock up. They work like a Detroit locker, where when I put torque on it, they lock. It locks these things all together. When I lift off, and when this is moving relative to this, then it allows these cams to move relative to each other. And the cams can slide over the pawls, and the pawls can kind of wiggle back and forth, and I can get the left and right hand side moving with respect to each other, and that's the differential action. So they can go around turns, and when you hit the gas, they lock. When you hit the brake, they lock too. They basically work like a somewhat smoother Detroit locker. Have a race car that has one of these. It shouldn't. Road racing cars should not have these. Really, I don't think anything should have these. It came from the front differential of a Honda four-wheel drive ATV. That's what we used in the Formula SAE team for a couple years in the early 2000s. And I don't know why that was selected. I think because it was small and light, which, weight matters a lot in racing, but having a good differential matters a lot in racing too. And that car behaves very strangely when you drive it. When you hit the gas, the tires lock, and when you hit the brakes, the tires lock. Which means that when you're doing braking, you really will have to brake all in a straight line, let off the brakes, and then turn, and then get turned in the direction you want to go, at the end of a turn and then plant the gas and the car will go straight. So it really puts power down amazingly well, and it brakes in a straight line amazingly well. But if you try to steer while braking, it wants to just plow and go in a straight line. And if you try to accelerate while steering, it wants to go in a straight line too. And in the middle of a turn, if you give it too much gas, it just kicks the whole back end of the car out and it spins. So once you're used to it, it's kind of actually fun, but not necessarily the fastest, smoothest thing. And there's really no way to adjust it. These things are known for eating themselves as they operate, so they don't last very, very long. Viscous slips, an interesting one. Here we just put on the input or output, or on the left or right, we put little fins that are splined to some fins are splined to the input, some of these little fins are splined to the output, and we put a shear thickening fluid in between here. So we put something like, imagine like cornstarch and water, where if it when you push hard on it, right, it gets the viscosity increases, but it'll still creep and flow with low shear. So you put something like that that's reliable and won't break down organically or something like that. And you obviously couldn't use cornstarch and water and something like this for very long, but you use the petroleum equivalent of a shear thickening fluid like that. And as these things move with respect to each other, you get torque transmitted from left to right, and it's viscous, right? So the torque transmitted is a function of the relative angular velocity between these omega and whatever the viscosity is of the fluid in between here. So essentially, it's some constant times the relative velocity between these is the torque transmitted. And there's not a lot of relative velocity between these things. There's a lot of surface area for shear. And again, you're using something that has a shear thickening properties here, so these shafts don't move a lot with respect to each other. So these are really simple. They use these in connecting the front and rear differentials on all-wheel drive cars and some applications. Jeeps use these for their center differential for a long time, certain kinds of Jeeps. And then some high-end like the old Lamborghini Diablo VT. That VT stands for viscous traction, I believe, and it was something like this to connect the front and back. So you see some of these, but they're going to get hot. You're going to have, when you have a relative velocity and a force, you've got heat generation, because force times velocity is power. That power is going into heat, and you got to make sure these things don't get too hot. So for sort of driving around town all-wheel drive, it's fine. For a race car or a really high-performance street car, you got to worry about trying to keep this thing cool. And then they make all sorts of crazy active ones. So there's different ways of doing it. I mean, essentially, you're just trying to get torque from the left to right. So there's all sorts of crazy gear and clutch mechanisms for doing this. Of course, my favorite probably is going to be where you use the brakes, because you've got a lot of this stuff already in your car. You've already got the brakes, you've already got the controller for the brakes, you've already got the sensors, and so you really can take stuff you've already got on the car, and as long as you have a fast enough 4-channel anti-lock brake controller, you can sort of do all sorts of fun things without needing mechanically complicated differential. But there might be some other tricks you can use on an active differential that might make it worthwhile. So there's some good applications. There's some less good applications. GM's got a pretty good active differential. Actually, one of our alum did a lot of work on their active differentials at GM. So that's it for differentials. Thank you all, and I will see you next time.